Everybody likes nice things. We dress up. We get excited about new iPhones. We appreciate art. And software engineers too. We take pride in producing good quality code. We want to build systems which are like well-oiled machines. We want to work with software that's just good. But real world isn't always like that. There's a lot of systems which are clunky, old, unpleasant, legacy systems. Here are some common ways of dealing with legacy systems. This is pretending that they don't exist. Or this is closing your eyes and hoping they'll disappear. They don't work. I'm Marek Kiszkis from Netflix, and I spend a lot of time working with legacy systems. Today, I'll share with you some tools that do work and hopefully help you envision the path to deprecating your legacy systems, which should be. Let's have a look at the agenda. First, we'll define the problem. What exactly are legacy software systems? What problems do they cause? Then I'll give you a general recipe for phasing out legacy systems. Finally, we'll dig deeper into some details of the process. So let's begin. What are legacy software systems? A software system, for the purpose of my talk, can mean different things. Usually, it's a web application or a microservice, but it can also be a component or a library. It's a self-contained unit of software which exists among other units, other systems. So, what's a legacy software system? It's a system that's been superseded, but is difficult to remove because of its wide use. So we want it gone, but it's still in use. Think about the different software systems you work with. They come in all shapes and sizes. There are bigger ones and smaller ones. And here's my addition to the official definition of a legacy software system. Legacy systems are the ones which are old, complex and convoluted, and unsafe. Engineers always complain about working with legacy systems. And why exactly is that? Do legacy systems really deserve such a bad reputation? Yes, they do. Every possible problem you can imagine, legacy systems usually have. Old technologies, no tests, no monitoring. They are hard to debug. Everything is hard to find. They mix unrelated areas of functionality. They use obsolete frameworks. They don't follow best coding practices. They are full of that code, and you never know what's going to happen when you make a change. So it's really obstacles everywhere you look. Should be no wonder now that engineers don't like working with legacy systems. It's like slogging through mud of tech debt. I will admit to some arrogance now. I would sometimes look at a legacy system and think, oh, this is so bad. Who built it like this? I think this is common we are looking for someone to blame. Here's the hard truth. Usually, there isn't anyone to blame. Software deteriorates over time. Deadline pressure, cutting corners, forgetting about to-dos. All of this compounds over time. Your systems are getting older, weaker, and more clunky. We don't upgrade to the newest frameworks. We keep testing manually. Original developers move teams. So this is just a fact of life. Software deteriorates over time. Legacy system, as Marie Kondo would say, has served its purpose and no longer brings you joy. So we're ready to say goodbye. To recap, legacy systems are old and riddled with problems. We're ready to pull the plug on them, but other systems around still use them. In the next section, I will present a way around this. I'll give you a recipe for phasing out legacy systems. First, let's look under the hood of a sample legacy system. Let's say it's a microservice which exposes different endpoints. We're not getting into details. I just want to point out two things. The application is composed of individual endpoints. And these endpoints have different characteristics. They vary in complexity. They vary in their interactions with the outside world. For example, only some of them do database writes. Let's now zoom out on the legacy application. Each cell represents a single endpoint. Colors group related functionality together. So perhaps the account management APIs we saw before correspond to green. Perhaps yellow is movie ratings, orange is favorites, and so on. So there are different parts of functionality, and a lot of that code shown in white. Now that we've established what our legacy system looks like, we can talk about deprecating it. But I want to leave the world of software for a minute, and I want to tell you about a really interesting plant. It's called the strangler fig. It's like a parasite which preys on other trees. It's a clever species whose strategy is to attach to and gradually replace the host tree. So we start with a regular tree. It's big, it's grown over many years, and then a strangler fig sapling attaches itself to it. First, it builds the tree trunk next to the original tree. Then it starts building branches. These branches form a tight network around the old tree. With time, the old tree gets strangled and dies. And all that's left is the strangler fig tree. I think this is amazing. We really can learn something from anything around us. At some point, one of us sat down in a jungle and studied the strangler fig behavior. And then they thought, I need to do this to my legacy application. The host tree is our legacy system. Because it's used by other systems, we can't just rip it out. We can't just remove it. We need a clever replacement strategy. Essentially, what we do is build a Strangler Fig application. Whatever part of our old system is needed, we rebuild anew in a Strangler Fig application. This new application gradually takes over. Eventually, the old application gets strangled and dies. I want to pause here for a bit. If there's only one slide which you remember from my presentation, it should be this slide, and the Strangler Fig application pattern. It's actually a real name used in software development. You might have heard about strangling an application. It's precisely this process. Thank you, the guy in the jungle. So how does it work in practice? Let's go back to our original application. The first step is to extract one part of functionality, let's say green, into a new application. We also put a lightweight routing component in front of the applications. Initially, all traffic is going to the old application. Once we have the green functionality ported over, we route the green traffic to the new application. This allows us to effectively strangle the green part of the old application. We repeat the same process, perhaps now extracting the orange part. Move the traffic, repeat. Eventually, everything which was still needed gets moved to the new application. Legacy application is now 100% dead code and can be safely removed. And that's it. One more important observation. Remember the problems we were facing with our legacy application? We have the chance to make it all better with the new one. We're not copy-pasting code. No, no, no. We clean up, we refactor, document, upgrade. We add test coverage. To the outside world, both applications look the same. They provide the same endpoints, the same functionality. But on the inside, in the new one, everything is sound and solid. To recap, we went over the Strangler Fig application pattern. We rebuild the necessary parts of functionality in a new application and gradually switch over the traffic to it. Eventually, the old application dies, and we only have the new one left. The world is in a much better shape than it was before. In the next section, I'll dig deeper into some details of this process. Let's look at an individual endpoint. Imagine this is the reset password API. On the left, we have the legacy implementation. On the right, we have the new one. Now, these boxes are meant to be interchangeable. We'll be switching the traffic from the old to new. So they should follow the same contract. But they might be different on the inside. In fact, they should be different because we are rewriting and upgrading and cleaning up. So if you think about it, it's really not clear at all that this switch is safe. How do we ensure that the old and new implementation is equivalent? What we want to avoid is, I think it's a common pattern that we run into sometimes. When you're making a change and you're just like, did it work? We want to do better than this. We have 3 different tools at our disposal to help ensure the safety of this switch. Each of them is applicable in different scenarios. The first tool is equivalence testing. It can only be applied for read-only APIs. A good example is the hasEmail API. There's no state change involved, so it's safe to run the same function twice. And that's what we'll do. Every time hasEmail is called, we run the old and new implementation, and we compare the results. We see how often they match and investigate the discrepancies. Any difference between the implementations will show up during equivalence testing. So, in other words, it's like what they do in movies when there's a guy and his clone, and you want to distinguish between the two. You ask them a lot of questions and see if they respond the same. And with legacy system deprecation, we want to build a clone that's undistinguishable on the outside, but much cleaner on the inside. Equivalence testing can be very useful, but it can only be applied for read-only APIs. If there is state change involved, we can't run the same function twice. In fact, we might not even have any responses to compare. A good example is reset password API, which should have been called update password. It writes the new password in a database and doesn't return anything apart from success or failure. A good approach to use here is retrofitting tests for this functionality. There are a few important scenarios for this API. Happy case, trying to update to an empty password, and so on. For each of these, we can write a test case, checking what gets written in the database and how errors are communicated. We then make sure that these tests continue passing with the new implementation just as they did with the old one. Here's where the problem is. You need to write test cases for all the important scenarios. So the peace of mind you get from this approach is proportional to your test coverage. It takes more work than equivalence testing. And there are still other cases where interactions between systems are extremely complex. The state change affects multiple data stores. It's hard to understand exactly what's going on under the hood. So it will be hard to write good test cases for such functionality. The last tool we have for ensuring equivalence is A/B testing. A/B testing is a way of measuring the effect of two variants of a single variable on the metrics we care about. We want to see how metrics change depending on variant A versus variant B. In our case, A versus B is old versus new implementation. We run the traffic, letting half of it go to the old implementation and half to the new implementation. And we collect and compare the metrics. Perhaps the metrics we care about are latency of this call and the success rate. If more of your systems are integrated with an A/B testing framework, you can compare more metrics. You can even track the customer over their journey throughout the next days or weeks and check the business metrics. So in this approach, we are saying, I don't really know what's going on in this box or this other one. I will compare them from very high level, just looking at the metrics I care about. If these metrics are about the same, the boxes are probably equivalent. It's too complicated to compare them at any lower level. So we went through 3 techniques for ensuring the safety of a switch from old to new. We can actually compare these approaches using the scoring rubrics that Shona and Dan described yesterday for engineering interviews. We can rank them on safety and how cheap the setup is. Equivalence testing gets 4 out of 4 in safety. It's very safe, compares everything. And 4 out of 4 in setup. It's very low cost. But it only works for read-only endpoints. Retrofitting tests gets 2 or 3 out of 4 in safety, and 1, 2, 3 out of 4 in setup. Everything depends on how many test cases we need to manually churn out. A/B testing gets 2 or 3 out of 4 in safety. We'll find out if things go wrong, but we're using live traffic. And 3 or 4 in setup. Everything depends on whether you're already integrated with an A/B testing framework. In the last part, I want to talk about the people involved in deprecation projects. Because legacy systems have such a bad reputation, people sometimes want to stay as far away from them as possible. I think this is not always rational. Yes, we saw that working on a legacy system is painful, but deprecating a legacy system is something that can be quite different. First of all, the Strangler Fig application is built from scratch. It's a blank canvas. Anything that was wrong with the old application, we can make better. It's your frameworks, your architecture, your coding practices. This can be very rewarding. 2, there's a prize waiting at the end. if the legacy system survived for so long, it means that either no one tried to deprecate it, or that all previous attempts failed. So you can become the champion who slayed the beast. And everyone who ever worked with this system will surely celebrate it being dead. And then we can watch for the bugs. But I also recognize that there are some qualities we should look for in people who take on deprecation projects. The first one is what I call simplification mindset. Dijkstra said that simplicity is a prerequisite for reliability. And if you think about it, lack of simplicity was the root cause for everything that was wrong with the legacy system. So it has to be simplified. Some people really enjoy untangling complicated messes. To me, it feels like a challenge, like the mess is staring me in the eye and saying, I bet you can't figure out what's really going on here. Yeah? Watch me. I think simplification mindset is one of the most important qualities overall in software engineering. The other very useful ability is communication and social engineering. We need to work with different teams to understand the historical context, to get some help in debugging, or we need them to make some changes. Being able to get others excited about your admittedly maybe not exciting cause is a very useful ability that will make it so much smoother. So in summary, we spent time today thinking about legacy software systems. We saw what they are, what problems do they cause. We went through a general approach for deprecating legacy software systems, Strangler-Fig application pattern. We learned 3 techniques that can help ensure the safety of the switch: equivalence testing, retrofitting tests, and A/B testing. Finally, we thought about the people. What can we offer them? A clean slate and a prize at the end. And what we're looking for, a simplification mindset and social engineering. I hope that with this, you no longer feel powerless about your legacy systems. I hope we shed some light on them and that you will be able to see how to deprecate them. Please tell me how it goes. Thank you.